So let's go ahead and draw out a picture of what's going on. So we've got two sources of light. Okay. I'm going to draw them. Well, what I'm going to do is let me draw out an axis system here for you first. So let's say this is like, I don't know, a road or, you know, along some floor in a house or whatever it happens to be. And so we've got two sources of light. We've got one guy over here. And then we've got another guy over here. And the only thing that we know, well, not the only thing, but one of the things that we know is that these guys are 10 meters apart. So this total distance from here to here, if I go ahead and I connect those guys, this length right here is 10 meters. Now we also have an object somewhere in between here. Okay, we'll call it x. Okay, where x is the distance. Okay, when I say we'll call that x, we're not really going to call the point x. What we're going to call x is the distance from one of the light sources. We'll call that distance x. Okay, so somewhere in here is some point, and its distance away from one of the light sources is x, which means that its distance from the other light source right here has got to be 10 meters minus x, like that. Now we have to go ahead and use some of the other information given. So we've got illumination, okay, which we're going to, let's just call that guy, I don't know, I, okay. So there's some illumination from light source 1. So I'll put that in that color. So the illumination from light source 1, let's say that's 4 times, okay, because it says it's 4 times the illumination from the second light source. So that'll be equal to 4 times the illumination from the second light source. So this is the the correspondence between the two illuminations. Now I use the lighter color, the more brighter color for the more illuminating light source, so the more intense. Okay, so you can think about I as intensity as well if you want to. It doesn't really matter here. Now, what we're trying to find is the darkest point on the line segment, okay? So we're going to try to take this point right here and stick it in the darkest spot according to its distance from these two point sources. So what we need is the amount of illumination from each, or the amount of light, right? So the amount of illumination from source 1 plus the amount of illumination from source 2, we'll just say that that's equal to, let me color code this again. So if I color code it, I've got that, and let's say that that's equal to what we want to find, which is the total illumination. Now it says that the amount of illumination from a point source is proportional to the intensity of the source and inversely proportional to the square of the distance from the source. So what that means is, it's hard to read, okay, but what it means is that the amount of illumination here from point source 1 is equal to some constant, I'm just going to call it K, some constant of illumination, times the intensity. Okay, so it's proportional. Okay, so I've got that right there. And it's inversely proportional. So inverse will divide by inversely. So here's what we mean. As the illumination, as the amount of intensity goes up, the total light amount will also increase by some constant. Okay, but it's inversely proportional to the square of the distance. So the distance from the point to this light source is x, so it's inversely proportional, meaning we divide by it, so as this guy goes up, this guy goes down. It's inversely proportional to the square. So we've got this right here. We also have the same for this guy, but the only difference is, so it follows the same proportion value times its intensity, but it's divided by the distance. Now the distance is 10 minus x squared, like that. So if we want to know the total amount of light or illumination at some point, okay, well, that's equal to L1 plus L2. So that'll be K I1 over x squared plus K I2 over 10 minus x squared, just like that. But we also know how I1 and I2 relate to one another. So we could write this as LT for the total is equal to K times, let's just go ahead and replace this guy in here. So I1's equal to 4I2, so that'll be times 4 times I2 over x squared plus K times I2 over 10 minus x quantity squared, like that. And so what we want to do is we want to minimize. Our goal is to minimize the light at our point, because we're trying to find the point along this line that has the minimum amount of light. So what we're going to do is we're going to take this function and we're going to find its minimum. Now, of course, I don't know what I2 is. Okay, so our solution will go ahead and involve that. Now let's take a look at the next problem. So let's go down here. So problem number 3, let's go ahead and read through that. It says, given 4 numbers a, b, c, and d, find a number x which best approximates them in the sense that the sum of the squares of the differences between x and each of the 4 numbers is as small as possible. So let's go ahead and take and write out what we know. Well, we have 4 numbers. Okay, so we've got A, we've got B, we've got C, and we have D. And we need to find a number x out there such that the sum of the squares of the difference between x and each of these numbers is as small as possible. So the sum of the squares of the differences. So what this means is we need to find some number x such that x minus a squared, so it's the difference between x and the number, okay, squared. Okay, so that's the first one. I suppose I could write these in the colors that I've got here. So this is going to be x minus a squared plus x minus b squared plus x minus c squared plus x minus d squared. We want to minimize this. We want to get it to be as small as possible. So what we're going to do is we're going to look to try to determine, we want to minimize the variable x. Well, we won't want to minimize the variable x, excuse me. We want to minimize this function. So this is going to be, well, I guess I could still call it, so we want to minimize that thing right there. Before I move on, the one thing that I should note is that the minimum of x is not x, because this is a new function. Okay, so this isn't equal to x, it's equal, we want to minimize this guy, so we can call it whatever we want. I'm gonna call it, I don't know, I'll call it, I don't know, let's do y. It really is irrelevant what I call it. Okay, but just know that this thing right here is not equal to x, but we want to minimize this guy according to some rule. Now let's take a look at number 4. For says, suppose that it costs x squared divided by 100 plus 10x cents to run your car for x days. Once you sell your car, it will cost you 50 cents a day to take the bus. How long should you keep the car? Well, this seems like a pretty non-realistic problem, but let's just go ahead and solve it so that we can work, or at least set it up so that we can work with solving this. So our cost as a function of x is equal to x squared over 100 plus 10x, where this is in cents and x is in days. It also costs us, so this will be cost function number 1. It also costs us for cost function number 2 as a function of, here's where we have to be a little bit careful. It's still as a function of x. Okay, but the cost doesn't kick in for this until after this guy's above 50 cents. So what we want to do is we want to use this. We want to use this guy right here until it is above this guy, because as soon as it passes this guy, then this guy is the guy that we want to use. So there's a couple ways that we can look at this. Probably one of the easiest ways to do this is to graph this function out. Okay, so to take, we'll do C1 in blue. So the cost in blue, this is a squared function. At the origin, it looks something like this. This right here is just a linear function for x days. So this tells me the total for x number of days. This just tells me the value on that day. So that would look like, if I went ahead and I put this guy here, if I graphed it out, it would look something like this. Okay. Now, what we're looking for is this guy, because for all the days up to this point, the cost is less than this cost. But after that point, switching is a good idea. The other way we could look at this is we could take a look at the derivative. And we could say for this derivative, okay, when is it going to be equal to 50? So when is the change? When is the change in cost 1 with respect to the change in time equal to 50 cents per day? So the derivative of this equals to the derivative of this. I guess I didn't really need to, well, it would look something like the derivative of this right here is something that looks kind of like, let's see here, it'll be linear, but it's going to be pretty flat, because the derivative of this right here, so C1 prime of x is going to be equal to 1/50th x plus 10. So that, I mean, that's got a real small slope, but it's up at 10 units. So it's going to look something like this. And of course 50 itself, the rate of change of this guy, 50 cents per day, is just flat. So I'll put it right here. It looks like this. So again, we're looking for something along those lines right there. Now let's stop here and let's go back and look at how to solve each of these in the next example set.